Hello. This video is the first in a series of 3 videos about functions of several variables and multiple integrals. This work will be divided into 3 parts. In the first part, we will talk about implicit functions, their derivation, and the calculation of the differential of an implicit function. As a discussion support, the first part consists of 3 exercises. The first is an exercise about directional derivatives and the relationship with the gradient of a function. The second exercise is about a function defined implicitly by a relation. It involves calculating the differential of an implicit function and approximating a function of 2 variables at a point using Taylor's formula. So we start with the first exercise, which is as follows. We assume that f of x, y, z is a function of 3 variables. We are given 3 vectors u, v, and w. We can verify that the 3 vectors are normalized, or unit vectors. We assume that at point ABC, we have the directional derivatives of f along the vectors u, v, w, given by the derivative of f. In the direction of vector u at point ABC is 0, the derivative of f. In the direction of vector v at point ABC is 0, and the derivative of f. In the direction of vector w at point ABC is equal to 2. Note that the function f is unknown. We ask to get the gradient of f at point ABC. Then the gradient of f is the vector, having as components the partial derivatives of f at point ABC. So the gradient of f at point ABC is the vector having as components the derivatives of f, partial derivatives of f at point ABC. So we are looking to calculate this gradient. And since the problem gives us the directional derivatives in the direction of 3 unit vectors, we will try to calculate the partial derivatives from the directional derivatives. So, what is the relationship between the gradient and the directional derivatives? Let's take a vector u equal to u1, u2, u3, unit vectors. Thus, the norm of u is equal to 1. In this case, the derivative of f in the direction of the vector u at point ABC is equal to the gradient of f at the point B, C, dot product u, dot product with u. In other words, we will, to simplify, denote the gradient of f at A, B, C as the partial derivatives we are looking for at the point A, B, C. We will call them alpha, beta, gamma. In this case, the derivative in the direction of vector u of f at point A, B, C thus becomes the dot product of this gradient with the vector u, alpha, u1 plus beta, u2 plus gamma u3. In the statement, we have the derivative in the direction of vector u of f at the point v is 0. We are looking for the gradient, which is the vector of e. So for this vector u, which is equal to u1 over the square root of 6, I look at this vector 1, 1, 2, there you go. So multiplied by 1, 1, 2. In other words, the derivative in the direction u of f at the point a, b, c is going to be equal to then 1 over the square root of 6 as a factor of a plus v plus to Gran. We take the dot product of vector u with the vector a, v, g, and this is 0 according to the text. Similarly, the derivative in the direction of vector 5 of f at point A, B, C is equal to 1 over square root of 3. And we will look for the components of v. It's 1 over square root of 3, 1 minus 1. Minus 1, which gives us here. So alpha times 1, then beta times minus 1, gamma times minus 1 equals 0. And finally, the derivative in the direction of the vector of f at point A, AB, C is equal to, and we will look at the vector W. It's 1 over square root of 3, 1, 1, 1, and 1, and 1. Which gives us 1 over square root of 3 alpha plus beta more gamma equals 2, because the text tells us that this derivative is equal to 2. So alpha and beta and gamma are solutions of the following linear system. So we have alpha more beta plus 2 gamma equals 0. That's the first one. We can remove the 1 over square root of 6. In the second equation, we have alpha minus beta minus gamma equals 0. And the last one, if we multiply by square root of 3, it's alpha plus beta plus gamma equals 2 square root of 3. So by grouping the second and the third, since we have minus beta minus gamma plus beta plus gamma, by summing them together, we get to a equals as expected, which gives the approximately equals. So A is equal to, therefore, in the first equation, we have beta plus 2v is equal to minus alpha, that is minus square root of 3. The second one gives us minus beta minus gamma equals minus square root of 3. And we clearly see that if we add member to member, beta disappears and we find gamma equals minus 2 square root of 3. By substituting, for example, in the second one, we have gamma equals alpha minus, beta is equal to alpha minus gamma, which, yes, gives us beta, therefore equal to alpha minus gamma, square root of 3 plus 2, square root of 3 equals 3 square root of 3. Finally, the gradient of f at point ABC. Note that f is not known. It is the vector square root of 3. 3 square root of 3 minus 2 square root of 3. So here is for the first question. So we have correctly determined the gradient of f at point ABC, even though we do not know f. Now, second exercise. We are given a function phi differentiable, a function of two variables u and v, and let z be a differentiable function of x and y. Z is a function of xy, implicitly defined by the relation f of x to z, y to z equals 0. Now we are asked to show that x multiplied by the differential of z with respect to x plus y multiplied by the differential of z with respect to y is equal to minus z. So here we know that z is a function of x, y. We can set z equal to g of x, and the relation that implicitly defines z becomes f of x2 z e squared y2. Z is equal to phi day of form x2 times g of e is e times bg of xy equals 0, which we can write in the form f2, a function that depends not only on x and y x2 times g of xy, we will call u of xy, and another function v e of xy g, which also depends only on x and y. We therefore want to calculate x times the partial derivative of z with respect to x plus y times the partial derivative of z with respect to y. We therefore need the partial derivatives of z as a function of xy with respect to x and with respect to y. We know that this function f is 0. So let's find the derivatives of z. This composite function f of u v with respect to x. Here we have the chain rule, which tells us the derivative. So we will call this function h of x equal to 0. So the partial derivative of h with respect to x at the point x, it's the derivative of this composite. So it's the derivative of f with respect to u at the point. So we go back to the beginning, x to z. To avoid writing x to g of xy, which is too long, y to z, multiplied by the derivative of the function u of xe with respect to x, plus the second term, which is the derivative of f with respect to v at the same point, x to z, y to z, multiplied by the derivative of the function v of xy with respect to x, which allows us to have equals therefore the derivative of f with respect to u, of course, at the point x to z, e to z times the derivative of u. So u is the function x to z. When we differentiate it with respect to x, it gives 2z. plus b x2 times the derivative of z with respect to x. We just differentiated x2z, which is a product. So the derivative of x2 times z plus x2 times the derivative of z partial derivative plus the derivative of f with respect to v at the point x2z, y2z multiplied is easy by the derivative of v with respect to x. So v, we revisit v. It's the function. y2z or y2g, it's the same. When we differentiate it with respect to x, there is only one term, which is y2g d of z over x. And all of this is equal to 0. So that was the derivative of h with respect to x. If we now differentiate h with respect to e, we find the same term, the partial derivative of f with respect to u multiplied by the derivative of u. So I remind you, u is x2's with respect to y. So as we differentiate with respect to y, we leave x2 derivative of z with respect to y. So there is only one term, plus the derivative of f with respect to v times the derivative of a to z with respect to y. This will give two terms, 2yz, since it's a product, plus y2, times the derivative of z with respect to y, and this is equal to 0. So in these two lines, the partial derivatives of z with respect to x will appear. We will group them. So for this, we will call the derivative of f with respect to u, we will call it a. The derivative of f with respect to here, it's at the e point x2 is O2 z, we will call it a, and the derivative of f with respect to v at the same point x2 is 2, so we will call it b. The two systems we obtain thus become a multiplied 1 by 2x, the first line on this page, plus x2 times the derivative of z with respect to x plus b multiplied by y2 times the derivative of z with respect to x. This is the first equation, and the second is a factor, 2x2, derivative of z with respect to y, plus b, factor 2yz, multi y2 times the derivative of z with respect to y. Here are the two equations that will give us the partial derivatives of z with respect to x and with respect to y. So in the first one, we can say the derivative of z with respect to x is multiplied by eax2 plus beta in group. The terms that contain these derivatives, there remains the term 2ax, or rather equal to minus 2x. In the second equation, we obtain the derivative of z with respect to y is multiplied by x2 plus b e squared, and the remaining term, we place it on the right side as minus 2b e z. And finally, we obtain the following partial derivatives as follows. So we have the derivative of z with respect to x, which is equal to minus 2x divided and by more by 2. And we have the derivative of z with respect to y, which is equal to minus 2 by z over a x2 plus beta by 2 is naturally calculated and possible if x2 more byte is non-zero naturally. Finally, we see that if we calculate x for the derivative of z with respect to x plus y for the derivative of z with respect to y, we then obtain the first is multiplied by thus minus 2ax 2z over x more by 2, then minus 2by2, since we multiplied by y over x more by, and we see x appear derivative of z with respect to x plus y derivative of z with respect to y equals, we see that we can factor out here minus z factor of x2. We have the same denominator plus bi2 divided moreover by dou x2 more by 2 with 2, which gives minus 2z, and this is indeed the formula requested in the text. X times the partial derivative of z with respect to x plus y times the derivative of z with respect to y equals minus 2z. We move on to the third and final exercise. In this third exercise, we have a function z, a function of xy. We assume that this function is given implicitly by the exponential relation 2z plus dbz is equal to x plus y. First question, find the differential of z of the function z. And secondly, use a linear approximation at the point 1, 0, to approximate the image of 0.99. 0.1, 0.1 by f, using, therefore, Taylor's formula. So we have here an implicit function defined by a relation, and we are looking for its differential. We are looking for its differential. So obviously, we do not know. We know that the differential of z is written as the partial derivative of z with respect to x dx plus the partial derivative of z with respect to y. We will therefore be led to find the partial derivatives of z with respect to x and with respect to y. So let's note that we have the following relation. Z is implicitly defined by the relation exponential of z plus 2yz minus x minus y equals 0. We will differentiate or partially derive this relation with respect to x and with respect to y. So we can call this g of xy. We can call this, therefore, g of xy equals 0. So by differentiating with respect to x, we obtain then 2 times the derivative of z with respect to x, well, exponential of z. Z is a function of x, y. Plus we differentiate with respect to x to y times the derivative of z with respect to x, and minus 1 equals 0. By differentiating with respect to y, the function g, we find 2 times the derivative of z with respect to y, exponential of z, more So there, 2yz. If we differentiate it with respect to y, it becomes 2z first plus 2y times the derivative of z with respect to y because it's a product. And the derivative of minus y is minus 1 equals 0. Here is what we obtain as a system. From there, we will derive the sought partial derivatives, and we find that the partial derivative of z with respect to x is equal to, we bring the 1.1 over the factor or exponential of the more 2i. And from the second equation, we derive the derivative of z with respect to y, also equal to, now be careful, 1 minus 2z, which we move to the second term over 2 exponential 2's plus also. So there you have it for the partial derivatives, and thus we have the sought differential dz is equal to 1 over 2 exponential of z plus of c greg of the c gregs of the c gregs of the c gregs c gregs of the c gregs of the c gregs c gregs of the c gregs c gregs of the c gregs dit more 1 minus 2 over 2 exponential of z plus y. Here is the differential of the function, which is defined implicitly and which we do not know. We now move on to the second question. Use a linear approximation, of course, of f2. Approximate the value f of 0.99, 0.01. So we will try to find this approximated value using Taylor's formula, which tells us that f of, we will put f of x plus dx y plus die. Taylor's formula to the order a, but we only take an approximation. We will ignore the last term. The rest is approximated by f of x, y plus the differential applied at the point dxd, or it's the derivative of the with respect to x at the point x, e dx plus the derivative of f with respect to y at the point x. So in our work here, the point z in question is the point 1, 0. So as we are at the point 0, 0, 0, 1. It is therefore a matter of taking dx equal to minus 0, 0, 1, and dy is equal to 0, 0, 1. And consequently, we need, of course, f of x, y, which is f of yin 0. So let's recall that z is defined by the exponential of z more 2z minus tam x minus it equals 0. If we substitute the point xy equals 1, 0, of course, here it's of Boixy. So here, by substituting the point 1, 0, we get the exponential of 2 times f of 1, 0, plus 2y equals 1, 0, times z, 0, z minus 1 minus 0 equals 0, which gives us the exponential of f of 1, 0 equals 1, or alternatively f of 1, 0 equals 0. And we find ourselves in the